Hello everyone, let's analyze. So last week we learned about what it means for a set to be compact. We learned about how it's related to open covers and convergent subsequences, and it essentially gives us a way of describing whether a set is closed and bounded and what properties such conditions would imply. Of course, the next thing we want to talk about is how do continuous functions retain, deform compact sets? So, our first theorem is one that you're familiar with because it was actually in your homework last week. Let D be compact and the function f on the domain D to R be continuous, then f is uniformly continuous. In other words, if you're continuous everywhere in a compact set, then you're automatically uniformly continuous. And of course the proof you're familiar with because you did it last week. In fact, it was the proof that was scaffolded in Wednesday's class. But since I'm here and you're there, let's give a different proof. The proof that you went over Wednesday got to its conclusion by using the definition of a compact set that every open cover permits a finite subcover. Could we prove it using the other definition of compactness? Let's give it a shot. Alright, so what do we know? We know D is compact, which the other definition says every sequence of entries in D has a subsequence converging to a point in D. What else do we know? We know f is continuous. Now, since we're taking a sequential perspective, let's give the definition of continuous that involves sequences. Remember that a function is continuous if and only if every sequence of points that converges to another point x in the domain, then f of xn converges to f of x. So that's what we know. Right? When we say that f is continuous and D is compact, that's what we're assuming in the hypothesis. Now, what is our goal? Well, we're actually going to prove this by contradiction. So our goal is to imply a contradiction, right? Our goal is to arrive at something that's absurd. So if we're going to prove something by contradiction, we're going to suppose that the hypothesis is true, but the result is not true, that f is not uniformly continuous. In other words, the negation of the uniform continuity definition is true. Now, it's really important that we understand what's meant by negating a sentence. And of course, we've all taken introduction to proofs. We know the mechanics of how to go through and negate. But let's just think it through step by step. So let's negate the definition of uniform continuity step by step. Now, I realize I'm being perhaps overly pedantic by going step by step and contradicting each logical quantifier, but it's important that we understand logically, intuitively what's meant. Okay, so to negate the definition of uniform continuity is just to say that the definition of uniform continuity is not true. In other words, it's not true that for every positive epsilon there's a positive delta, for which every x and y in the domain within delta of each other implies that f of x and f of y are within epsilon of each other. And so that's not true for every epsilon. Now, if it's not true for every epsilon, that means there exists an epsilon for which the remaining part of the definition is not true. In other words, there exists an epsilon greater than 0 for which this is not true. That there exists a delta greater than 0 for which every x and y in D within delta of each other implies f of x and f of y are within epsilon of each other. So what does it mean? That it's not true that there exists a delta? Well, there exists an epsilon, and if it's not true that there exists a delta, right? That means for every delta, the remaining part is not true. Because in the previous, I said it's not true that there exists a delta. In other words, for every delta, what follows is not true. And what follows? Well, that there's an x and y in the domain within delta of each other, implying that f of x and f of y are within epsilon of each other. So if this statement here is not true for every delta corresponding to an epsilon, then there exists an epsilon greater than 0, for which for every delta that's greater than 0, there's a corresponding pair of values x and y and d, for which this is not true. Whenever x and y are within delta of each other, f of x and f of y are within epsilon of each other. Well, if that's not true, if every x and y within delta of each other implies f of x minus f of y is within epsilon of each other, if that's not true, it means that there is an xy within delta of each other, but f of x and f of y are not less than epsilon. And of course, if f of x minus f of y is not less than epsilon in absolute value, then the absolute value is greater than epsilon, or equal to. So that last bullet is the negation of uniform continuity. Right? There exists an epsilon where everything fails. What does it mean everything fails? It means for every single delta, there's a corresponding pair of values x and y that are within delta of each other, but f of x and f of y are greater than or equal to epsilon. So, of course, the last bullet is all we need, right? We're supposing that f is not uniformly continuous, which means that last bullet is true. But it's important, more than just the machinery of changing for all to there exist, it's important that we understand logically, intuitively what's meant when we negate a sentence or when we negate a statement. Now, in this last bullet, there's a for every delta. Whoa. The notes almost try to run away on me. For every delta greater than 0. Every single delta. In other words, every positive number. Well, 1 over n is a positive number. If n is a natural number, right? 1, 2, 3, 4, so forth. So, for every 1 over n, there are values x and y and d that correspond to the choice of delta. Let's label those values xn and yn. So, that last bullet means there exists an epsilon greater than 0, so that for every natural number n, there's a pair of values xn, yn, and d, for which xn minus yn is less than 1 over n, and f of xn minus f of yn is greater than or equal to epsilon. So this is essentially what supposing that f is not uniformly continuous has bought us. That these values exist, xn and yn, they exist. For every natural number, xn and yn exist, and this statement is true if f is not uniformly continuous. So the question we must ask ourselves, is that highlighted statement compatible with f being uniform and d being compact? Well, of course it isn't, because we're trying to prove this by contradiction, and I wouldn't have taken you this far if it wasn't going to work. Now, since d is compact, the sequence of values xn for n equals 1 to infinity, right? That's a sequence of values in the domain, and it has a convergent subsequence because d is compact. And the convergent subsequence has a limit x, and that limit x is in d. Now, notice that the entries of the subsequence y that correspond to the entries I picked out of x grow arbitrarily close to the entries of the subsequence of x. Right, remember, if I pick the same indices, because that's what a subsequence is, I'm removing certain indices. So if I pick indices to generate a subsequence of x, if I choose the same indices of y, the difference between x and y of the same index is 1 over that index. That's this statement here. They grow arbitrarily close to each other. So if x n of k and y n of k are arbitrarily close to each other, because one of n can be made arbitrarily small, and x n of k converges to x, well then y n of k must converge to x. Now you see here there's a footnote, okay? Hopefully that idea makes sense to you, but that fact is actually proved rigorously here in the footnote, so I encourage you to read that. But the idea, I hope you see, is simple. Xn is a sequence of values. Compactness buys me that it has a convergent subsequence. If I choose the same values of y, they're arbitrarily close to the subsequence of x entries. Therefore, wherever the subsequence of x entries converge to, so must y. Okay. So then the limit as k goes to infinity of f of x n of k and f of y n of k have the same limit, f of x, because f is continuous. Right? When f is continuous, if x n of k converges to x, f of x n of k converges to f of x. And since y n of k converges to x, the limit of f of y n of k converges to f of x. But this contradicts the fact that f is not uniformly continuous, because f of xn minus f of yn is always, for every n, bounded below by a positive number. In other words, it's not possible that this gets arbitrarily close to the same thing as this, and that they have the same limit if f is not uniformly continuous, because assuming that f is not uniformly continuous implies that those sequence entries never get arbitrarily close to each other, because they can never get less than epsilon to each other. So they can't have a common limit. But that contradicts the fact that f is continuous. And we've found our contradiction, and we've proven the result. Now, here's where aesthetics comes into play. We just went through one proof by using the definition of a compact set as being a set where every sequence of elements in the set has a subsequence that converges to a limit in the set. But in class and in your homework, you proved the same result using the fact that the domain is compact if every open cover permits a finite subcover. So, where does aesthetics come into this? Well, which proof was prettier? Which one was more elegant, more simple, more concise? Which one is more intuitive? Which one felt better? Which one looked better? Do you have a favorite proof? I have one. What is it? I'm not going to tell you. I don't want to influence or bias your choice. Now, a quick historical note. The proof that we went through and the proof that you went through in class was actually one of the most important feats of math in the previous, well, I guess previous to previous century, in the 19th century. it wasn't clear when people started thinking about these ideas how exactly to prove this result and how to do it in a way that was concise and straightforward and would convince other mathematicians. It actually took the careers of several historically important mathematicians to prove what you did in your homework. Remember, you know more calculus than Newton did. Now, among math historians, there's some disagreement about who proved the theorem first. Bolzano wrote a book called Function Theory in 1830 that had ideas for the proof that you did in your homework. He took the open sets approach, but the book wasn't published in 1930. But Bolzano and Hein of Hein-Borel fame, also did proofs, and Hein published his in 1870. Bolzano did his in 1830, but it wasn't published in 1930. But both, of course, are giants in mathematical history who worked on what you're working on. Well, that's it for today.